Hello, this is Professor Roman, and we will continue with our look at linear algebra. I should mention first that if you are interested in the book that accompanies these lectures, or the notes that accompany my transition course, also on YouTube, or just if you're interested in learning a little more about me, you can visit my website, www.sroman.com. So today we're going to discuss some preliminaries that are extremely important for the study of linear algebra. And some of these you may be familiar with, but others you certainly may not. So we begin with the notion of a multiset. By definition, the elements of a set do not appear more than once. But sometimes it's convenient to consider collections in which an element can be repeated. And these are called multisets. The concept of a multiset is very useful at times, but doesn't seem to get much attention, which I think is a shame. We will need only a more or less informal definition of a multiset. A multiset M is a collection of elements in which each element can appear more than once. The number of appearances of an element is called its multiplicity. And the set of elements that appear in the multiset, not counting their multiplicity, is called the underlying set for the multiset. So here's a simple example that will clarify. This is a multiset, A, B, C, C, C. If this were a set, it would just be the set containing A, B, and C, because you don't allow duplicates. But as a multiset, the element A has multiplicity 2, the element B has multiplicity 1, and C has multiplicity 3. The underlying set is ABC. Multisets, for example, play a role in describing the roots of a polynomial. For example, this polynomial, which can be factored, has root set, just the singleton set 2, but it has root multiset 2, 2, because 2 is considered a double root. So it's a root of multiplicity 2. For two multisets to be equal, of course, their underlying sets have to be the same, and each element has to have the same multiplicity in each of the multisets. Collections or families of sets are quite common in mathematics. For example, the family that I denote SUB of Rn of all subspaces of the vector space Rn, and more generally the family of all subspaces of any vector space, play a key role in the study of vector spaces, and we're going to spend quite a bit of time studying sub V. The subspaces of V, we'll see that these have their own algebraic structure called a lattice. Families are often, but not always, written in indexed format. So this is an example of what an indexed family would look like. F is the set of all A sub I. These are subsets of a universal set X, I, and I. There are situations where we want to allow duplicates in families of sets or families of any kind of elements. Actually, as I discuss in the transition course lectures, in mathematics, everything is a set, or what is referred to as a proper class, which we don't need to go into at this moment. But basically, the elements of sets are other sets. So in that sense, all elements are sets. So when I say family of sets, that's as general as it gets. Families of integers are sets. Families of real numbers, sets of real numbers are sets, and so on. There is some inconsistency, however, in the way the terms family and collection, which is a synonym for family, are used. Sometimes the terms are synonyms for set, sometimes for multiset. So when you read in any book, let F be a family of sets, you have to check and see whether the author is allowing duplicates or not allowing duplicates. An indexed family or indexed collection for us will be a multiset. So it'll look like this. F equals the multiset of all a sub I ranges over an index set, capital I. So it is quite possible that for different indices, I and j, the elements a sub I and a sub j are equal. We will not exclude that possibility. If we want to exclude it, we'll say so specifically. Next topic is Bezout's lemma. This is one of the most useful facts about the integers. If a1 through an are integers with greatest common divisor d, then d can be written as a sum of products like this, a linear combination. Alpha 1 through alpha n are other integers. So that the greatest common divisor of any set of integers can be written as a sum in this form. And this is called Bezout's identity. The most important case, at least for us, is if a1 through an are relatively prime, then their greatest common divisor is 1, and so we will have this expression. But conversely, if the integers a1 through an satisfy an equation like this, then they must be relatively prime. So this is an if and only if. And we will use this fairly often, usually for 2 integers, but sometimes for more than 2. The Bezout coefficients are far from unique, and you can add, in this example for 2 integers a and b, you can add rba and subtract rba, and so you can change the coefficients and still get the same quantity. Okay, so the coefficients, the Bezout coefficients, the alphas here, are by no means unique. Polynomials. As I mentioned in the previous lecture, we'll assume that you're familiar with the basic properties of polynomials. We're going to be discussing polynomials over arbitrary fields, and I'll describe and discuss fields a bit later. But you can, for now, think of f as either the real numbers or the complex numbers. The family of all polynomials in a variable x with coefficients in a field f will be denoted by f square bracket x. This is very common notation. F is called the base field, and a polynomial in f square bracket x is said to be a polynomial over f. So here's a typical polynomial. if a sub n here is non-zero, then it is called the leading coefficient of the polynomial. A polynomial is monic if its leading coefficient is 1. And this is going to be very important for us. Most of the polynomials we're interested in are monic. The degree of this polynomial, as long as an is not 0, the degree is n. And we'll set the degree of the 0 polynomial to be negative infinity. A polynomial p of x divides a polynomial q of x if there is a polynomial f of x for which q of x is equal to f of x times p of x. So another way to say that is q of x is a polynomial multiple of p of x. And then we use this same symbol we would use in the case of integer division or divisibility, proper term. A non-constant polynomial, p of x, is said to split over a field f if p of x can be written as a product of linear polynomials. They don't have to be distinct. So as you may know, all complex polynomials split over the complex field that can be factored into a product of linear factors. Over the real field, that's not the case. X squared plus 1, for example, is a real polynomial, and it does not split over the real field. It splits over the complex field. We can define relative primeness for polynomials the same way we do for integers. A set of polynomials, p1 of x through pn of x, are relatively prime if their greatest common divisor is 1, and pairwise relatively prime if when you take any two polynomials from this set, they are relatively prime. So that would look like this. And this will be very important to us as we study canonical forms. There's a version of Bezout's identity for polynomials that looks exactly the same as the previous version for integers, except we deal only with polynomials. Polynomials have two properties that are very important and sometimes mistakenly viewed as the same, and they are in fact different. They're totally different, but they happen to be equivalent. So if p of x is a non-constant polynomial over f, then it's irreducible if it has no non-constant proper factors. So you can't factor it into two polynomials, both of which have smaller degree than the original. So if p of x equals a of x times b of x, then one of the two factors must be constant. P of x is prime if whenever it divides a product, it must divide one or the other of the factors, possibly both. So these are two entirely different concepts. But for polynomials, a polynomial is irreducible if and only if it's prime. And so there are students who often think that these are, in fact, the synonyms, irreducible and prime, when they are not. They are totally different. For integers, they have the same definitions, the analogous definitions, and the same fact. An integer is irreducible if and only if it's prime. You can also apply the fundamental theorem of arithmetic that holds for polynomials. Every non-constant polynomial can be written as a product of irreducible or equivalently prime polynomials. This is called the prime factorization of the polynomial. And just as for integers, it is unique up to the orders of the factors, but also up to multiplication by a scalar. We're going to use prime factorization in a very important way. It's the key to understanding the structure of linear operators. And we'll be using it quite often, but it'll come much later in the course. Euclidean and unitary spaces. I'm going to assume you're familiar with Euclidean space of dimension n, Rn. The elements of Rn, the vectors in Rn, are ordered n tuples, and there is a standard inner product, or sometimes called the dot product, and it's defined this way. We're going to use this symbol for the dot product or inner product on Rn, and for other inner product spaces when we discuss them later in the course. The complex counterpart of Euclidean space is called unitary space, Cn. This consists of ordered n tuples of complex numbers. And there's also a standard inner product, and it looks very similar to the one for Euclidean space, but you must put complex conjugates on the second components, the components of the second vector. Okay, otherwise you don't get the nice properties that you want of an inner product. And all that we'll discuss when we discuss inner product spaces. It's the second part of this course. In general, we will write the elements of Fn. Again, F can be any field now. So Rn, Cn, or other spaces. We'll discuss all that at the appropriate time. We write them as column vectors. That's traditional. But this takes up a lot of extra space, especially for inline text. So we also will use row notation. But the difference between these two is purely notational. They're the same element of Fn. Cartesian products. I think you probably know that if you have two sets, S1 and S2, the Cartesian product is simply the set of ordered pairs. The first component comes from the first set, second components from the second set. We can easily generalize this to the Cartesian product of a finite sequence of sets. These are ordered n tuples. And this is the notation we'll use for the Cartesian product. There is no reason why these sets have to be distinct. In fact, sometimes you'll want them to be the same set. When you have a Cartesian product of n factors of the same set, S, we often write that using exponential notation, s to the power n. We can take one more step in generalizing to an infinite sequence of sets, and we can form its Cartesian product. And that consists of the infinite sequences of elements where the ith component comes from the set S sub I. further notation, okay, matrices. Again, I'm going to assume you know how to add and subtract and multiply matrices. Take the inverse of a matrix using Gaussian elimination. The basic coverage of matrices you'd find in a freshman or sophomore level linear algebra course. But let's set a little bit of notation now. We'll use...
I think you want to hear the song a little bit harder now.
Oh, sorry about that. It's my Alexa, and it likes to talk to me. It misunderstands mathematical terms and thinks I want to play music. So I've turned it off. Hopefully that won't happen again. The set of m by n matrices with entries in a field F will be denoted by m sub m comma n of F. So the subscripts give you the number of rows and the number of columns. And when those two are equal, we can just write script m sub n of F. We'll use two notations to denote the entries of a matrix. The ijth entry of a matrix capital A, I'm going to denote by capital A sub I comma j. But I also, on occasion, will need to write this capital A equals little a sub ij in parentheses, and that denotes the fact that A is a matrix and little a sub ij is the ijth entry. So both of these are very common notations, and they're both handy at different times. The ith row of a matrix A I'm going to denote by A sub I in parentheses, and the jth column by A super j, also in parentheses. If you see an expression like this for a matrix A, it means that the C1 through Cn, the C's are the columns. The vertical bars are a tip-off. That C1 through Cn are the columns of A. And when I want to emphasize the rows, I will write something like this. Okay. The identity matrix of size n by n, or just size n we'd say, is denoted by I sub n. And here are some terms related to square matrices. They can be used for non-square matrices, but it's much less important, so I won't bother with that. The main diagonal of a matrix, and here's an example, consists of the elements whose indices are I comma I, same row as column, so that goes right along this diagonal. The main subdiagonal looks like this. It's the entries just below the main diagonal. And the main superdiagonal looks like this. It's the two, in this case, two entries directly above the main diagonal. Any matrix obtained from a matrix A by removing 0 or more rows and or columns is called a submatrix of A. So this is the original matrix A, and I remove the first and third rows, I get a submatrix B. If I remove the second row and the second column, I'll get this submatrix. Because I said 0 or more, probably don't need this, then a matrix is a submatrix of itself. Just part of the definition. The trace of a matrix is a very simple concept, but surprisingly useful at times. The trace of a square matrix is just the sum of the entries on the main diagonal. And the trace has some interesting properties. It's linear, which means the trace of a linear combination of two matrices is that same linear combination of the traces. Also, even though matrix multiplication is not commutative, so AB is generally different from BA, their traces are the same. I'm not going to prove these. I'm not doing much in the way of proofs here because this is background information. You might want to try to prove that yourself. It's a good exercise in using the definition of matrix multiplication. Another interesting property of the trace is called a cyclic property. The trace of ABC is equal to the trace of BCA. It's cyclic because what happens is you take A and you move it from the beginning to the end, and you get this. You could then move B, and so this would equal the trace of CAB as well. Okay. On the other hand, unlike the determinant, the trace of a product is not the product of the traces. Transpose, the transpose of a matrix is obtained by converting the rows into columns. So officially, if A is an m by n matrix over F, then A transpose, which I'll denote with a super T here, is defined by saying that its ijth entry is the jith entry of the original matrix. So we interchange row and column indices. A matrix is symmetric if it's equal to its own transpose, so it's going to have to be square for that to happen, and skew symmetric if its transpose is equal to the negative of the original matrix. Here's an example of a matrix and its transpose. Each row becomes a column. Properties of transpose. Transpose is an involution, meaning you apply it twice, you've done nothing. It's linear, as is the trace. The transpose of a product, AB quantity transpose, is B transpose, A transpose. Don't forget to swap the order. It's the same thing as taking the inverse. You swap the order. The determinant of a transpose is the same as the determinant of the matrix itself. Matrix rank. I assume you've had some familiarity with this. The row rank of a matrix is the dimension of the subspace spanned by the rows, and the column rank is the dimension of the column space, which is the subspace spanned by the columns. And one of the most famous theorems in elementary linear algebra is that for any matrix, the two ranks are equal, the row rank and the column rank. The row space and the column space are generally totally different. In fact, if the matrix isn't squared, those two subspaces don't even belong to the same parent space, but their dimensions are the same always. There's just when you write a matrix, there is in fact a subtle relationship between the rows and the columns. And so if the rows span a subspace of dimension 5, then so do the columns. Diagonal and triangular matrices. Certain types of matrices are particularly important because of their matrix geometry, which in loose terms is the number and location of zeros. So where the non-zero elements are congregated, you might say. Okay. And we're going to describe several matrix geometries that are important in linear algebra. The first two are diagonal matrices. So those are matrices that are square, and the only non-zero entries allowed are on the main diagonal. They don't have to be non-zero, but nothing off of the main diagonal is allowed to be non-zero. Everything off the main diagonal must be zero. And the way I denote that is with, rather than try to fill in a bunch of zeros, I just use a large zero above the diagonal and below the diagonal. And that means that all of the missing entries are zero. A square matrix is upper triangular if everything below the main diagonal is zero. So that's what this big zero tells us. On or above the main diagonal can be anything, zero or non-zero. So for that, I'm going to use a large asterisk, which means the missing entries, in this case above the main diagonal, can be anything. I don't know, maybe I don't care. Lower triangular is defined similarly, but you put the star down here and the zero up there, because everything above the main diagonal must be zero. It is going to be extremely useful to introduce a notational device for matrices called the block form of a matrix. So just to give you an example, consider this matrix. It's got 4 rows and 3 columns. If we partition the matrix into submatrices by drawing some vertical and horizontal lines, we can draw any number of vertical lines, any number of horizontal lines between the rows and columns, as I've done here. Then we refer to each submatrix as a block of the original matrix. So in this example, we have partitioned the matrix A into 4 blocks, and here are the individual blocks. So we can write the matrix in what we're going to call block form by writing it this way. Just to be clear, because I referred to these as submatrices, there are brackets, parentheses around each of these. But in here, you just place the entries so it looks like this. Okay? So just to be absolutely clear, if I were to draw this matrix, this would not be the same as the block form of A. This is a totally different matrix. It's a different species. This is a matrix whose entries are matrices. It's a 2 by 2 matrix whose entries are matrices. That's not at all what we're talking about. We are simply taking the original matrix, 4 by 3 matrix, and drawing these lines to consider the submatrices separately. We have not changed the matrix in any way. This is a notational device. This is exactly the same as this, but written in a different notation. And so I'm going to subscript these matrices by the word block most of the time, not always, to help you remember that B1, B2, B3 are submatrices of the matrix A. Not entries of A, but submatrices. Even if, say, B1 was size 1 by 1, it's still a submatrix of the matrix A. This is how block form would look in general. We draw 0 or more horizontal lines between rows, vertical lines between columns, and partition the entries into submatrices. Perhaps the greatest virtue of using block form is that matrix algebra can be performed as though the blocks were actually simple entries, even though they're not. Of course, the blocks have to be compatible with the matrix operations. Let's take a look at an example. Here are two matrices written in block form. They happen to have 4 blocks each, 2 blocks by 2 blocks in both cases. If I want to take the product of these two matrices, I don't have to go back down to the entry level as I would usually do. I can actually multiply the blocks according to the same procedure I would use for ordinary multiplication. So you take the first row, multiply it by the first column to get the first entry. A1, B1 plus A2, B3 goes here. And the rest is obvious then. So there's no reason a priori to expect this is going to give you the actual matrix product, but it does. And I'm not going to prove this because, as you might imagine, having to do it with general block forms could be a bit messy. So I'm just going to give you an example. Here is a matrix in block form. Here's another matrix in block form. Ordinary non-block multiplication gives this. I checked it by computer. To verify this formula, I'll just compute the first entry. So A1, B1 plus A2, B2 looks like this, simplifies to this. And if you will notice, 17, 25, 38, 61, that's exactly these 4 entries. And the other entries can be computed in the same way. Okay. So this, in fact, does work. But notice that the blocks have to be compatible. So A1, B1 here, this is A1 and this is B1. If they were not compatible, if the number of columns of A1 was not equal to the number of rows of B1, you couldn't even take this block product. A1, B1 wouldn't be defined. So you can't just take two matrices, chop them up any way you want into blocks, and expect this to work. There has to be compatibility. If you look at this one, this is block A2, and this is block B3. You can take A2 times B3. It's this times this, and those are compatible for multiplication. Okay, because the number of columns here equals the number of rows here. Okay, so that's the only constraint on this. One of the cases that will come up often as we discuss canonical forms, and even before that, I try to get these pages apart. I always hate it when the pages stick together like this. Okay, here we go. One of the most common cases we'll encounter of block form, I'm trying to avoid saying block matrix because that implies somehow it's different from an ordinary matrix. This is simply a matrix written in block form. Okay? So this is a common occurrence. We're going to see a lot of matrices that have this block form. If I square this matrix, then according to the formula we just discussed, I'll get, I take this row times this column, it'll be b squared plus whatever this represents times the 0 submatrix. So I've written it this way, and then first row, second column, and so on. And when you clean this up, you will get this. Now this asterisk represents arbitrary unknown values. They may be different values than we have in these matrices, okay, or in the matrix A. So the asterisk entries may have changed, probably will. But the point is that this has the same block form as this. It has an asterisk and a 0. And we have squared the two diagonal blocks. More generally, we can raise A to any power, and it looks like this. So all we have to do is raise the diagonal blocks to that power, keeping in mind that the asterisk here may represent different elements than it did before. Even more generally, for any polynomial, p of x, with coefficients over the same field as the matrices, we can take p of a by taking p of b and p of c and sticking them in like this. So this can be quite an important technique for taking polynomials of matrices when they have this particular block form. A square matrix that has this block form, so we would refer to these as the diagonal blocks. Zeros everywhere else is called a block diagonal matrix, as opposed to simply a diagonal matrix. For this to be diagonal, all these blocks would have to have size 1 by 1. So here is an example. I've got 3 diagonal blocks of different sizes, but outside of these 3 blocks, everything is 0. So that's block diagonal. Similarly, block upper triangular would look like this, where above the block diagonal can be anything, but below must be 0. So to give an example, I took this one and I simply changed one of these zeros to a non-zero entry. This is block upper triangular. Everything below the block diagonal is 0. Elementary row operations. I will assume that you are familiar with these, that you're familiar with Gaussian and Gauss-Jordan elimination, elementary matrices, and so on. But just to set terminology, oftentimes the 3 elementary row operations are referred to as type 1, type 2, and type 3. I don't like that because I'm not always sure which one is which, and some authors, I think, use these terms differently. So I just replace these terms by row scaling. Simply means multiplying a row of a matrix by a non-zero entry, in this case the ith row. Row interchange, we interchange 2 rows. And row adjustment, where you add a multiple of one row, in this case the jth row, to the ith row. And of course there are the corresponding elementary column operations. This is the definition of row echelon and reduced row echelon form. I'm not going to go through that. I just added it here for completeness sake. Some basic facts about applying row operations. Two matrices are said to be row equivalent, and I'll denote it this way. If one of the matrices can be transformed into the other by a series of 0 or more elementary row operations. Because elementary row operations are reversible, it doesn't matter whether I say A can be transformed into B or B can be transformed into A. Each one implies the other, so we can simply say the two matrices are row equivalent. More generally, row equivalence is an equivalence relation. It is reflexive, symmetric, and transitive. I'm going to talk briefly about equivalence relations a bit later, but I expect you've seen this concept from your transition course. As to determinants, I'm also going to assume that you are comfortable with the basic concepts. The determinant of a product is a product of the determinants. A matrix is non-singular if its determinant is non-zero. The determinant of an upper triangular or lower triangular matrix is simply the product of the entries on the main diagonal. If any two rows of a matrix are identical, their determinant is 0. Or more generally, the rows or columns of A are linearly dependent if and only if the determinant is 0. Here's one that you probably haven't seen. A square matrix that has this block form, block upper triangular, or lower triangular would work too. The determinant of such a matrix is the product of the determinants along the diagonal. So this is another example of the power of block form All you need to do to compute the determinant of A is compute the determinant of the diagonal blocks and multiply. Let's look at the proof of this. It's going to prove to be very important, so we'll take a look at the proof. Actually, the simplest proof comes from the permutation definition of the determinant. As you may or may not know, there are 3 definitions for the determinant of a square matrix. The one you have seen, no doubt, is expansion by cofactors. Expand by a row or expand by a column. It's an iterative process for computing determinants. And it's the method that is generally discussed in a freshman-sophomore linear algebra course. But there are 2 other definitions, and I have included a topics chapter that describes the 3 definitions and shows that they are equivalent. It's a bit of work, but can certainly be done. But I'm not going to assume that you're familiar with one of the other definitions, which I call the permutation definition. So we will use the expansion definition that you do know for the proof, and that's why the proof is somewhat lengthy. It proceeds by induction on the number of blocks, which I'll call M. So I probably should change this N to an M to be consistent. Okay. When there's only one block, there's nothing to prove, because then it says the determinant of A is equal to the determinant of A. Okay. So we can suppose that M equals 2, so A looks like this, just 2 blocks on the diagonal, on the block diagonal, I should say. And let's suppose that the block B has this form. So these are the actual elements. It's size K by K. We again have to appeal to induction, but this time on the size of this block, on K. So we've fixed M at 2. This is in the outer induction that we're performing, and within the outer induction we need an inner induction. Okay, so when K equals 1, this has size 1 by 1, and if you look back here, this will then just be a single entry. So the first column will have that single entry, B11, and all zeros. So we can expand along the first column, and we will get B11 times the determinant of C, and that is in fact this. So I'll let you ponder that. But when K equals 1, all we have to do is expand along the first column, and we'll get this formula. So now we suppose that this result is true for K bigger than or equal to 1, and let B have size K plus 1 by K plus 1. Expanding this determinant of A along the first column gives this expression. Determinant of A is B11 times the determinant of the matrix we get by crossing out the first row and the first column. So I wrote it this way. I like this notation. I've never seen it anywhere else. And I'll write it more generally like this. This symbol which I didn't write all that well, it looks more like that, or sometimes like this, is the logical symbol for negation. It's read not. So this is A, not the ith row, not the jth column. In other words, it's A, take A, remove the ith row, remove the jth column. So that's what this notation is. Remove the first row and first column, minus B21, that's the next entry in the first column here, times this determinant, remove the second row and the first column, and so on. This is the expansion of A along the first column. There are terms corresponding to B11 through BK plus 1. Each submatrix A, remove row I, remove column 1, has block form consisting of 2 blocks. The upper left block has size k by k, and so the inductive hypothesis implies that the determinant of this matrix is the product of the diagonal of the determinants of the diagonal blocks. So this can be substituted into this expression. Determinant of A then looks like this, and determinant of C comes out, and this product, this sum, I should say, is the determinant of B. And so that proves that that completes this inner induction and shows that this formula holds when m equals 2. That was the hard part. Once we know this holds for m equals 2 for 2 diagonal blocks, we can take an arbitrary block upper triangular matrix and partition it into 2 blocks, two diagonal blocks. Okay? And so we can appeal to the inductive hypothesis to finish the proof. Okay, so this is a little bit of a unpleasant proof. That is often the case in dealing with determinants, in particular the expansion definition of determinants often requires an inductive. Since the expansion definition, expansion by cofactors, expansion by minors, same thing, is an iterative definition. It defines the determinant of an n by n matrix in terms of determinants of n minus 1 by n minus 1 matrices, one smaller. Proofs involving, or discussions involving this expansion definition, often inductive.